What if I told you Hubble's final image didn't reveal a new object? It revealed a forbidden number, a number that makes two of humanity's best cosmic rulers disagree by about 9%. One ruler says the universe expands at about 67 kilometers per second per megaparsec. The other says about 73. That gap is so stubborn, it's forcing scientists to ask the scary question: are we missing a piece of reality? Here's why this should be impossible. The early universe leaves behind a receipt: the cosmic microwave background, a baby picture of space. With our standard model of cosmology, that baby picture predicts what expansion should look like today, and it lands near 67. Then Hubble measures the present day using real stars and exploding supernovae, and it lands near 73. That's like two GPS systems disagreeing on your location by miles, except this GPS decides the universe's entire history. Scientists expected the gap to shrink as data improved. Instead, it held its ground. So, what's happening? Is Hubble wrong? Is the Big Bang model missing an ingredient? Or is the universe hiding a new force? To understand why this is a crisis, you need the normal science. What should happen? You can't stretch a tape measure to a galaxy, so astronomers build a distance ladder. Step 1. Cepheid variable stars. They pulse brighter and dimmer like a heartbeat. The pulse period tells you their true brightness. If you know true brightness and you measure apparent brightness, you get distance. Step 2. Type Ia supernovae. These explosions are so bright they can outshine entire galaxies. Calibrate them using Cepheids in the same galaxies, and now you have a ruler that reaches much farther. Step 3. Combine distances with how fast galaxies appear to recede, and you infer the present-day expansion rate, h0. Now, the other ruler, Planck and the early universe. Planck measured patterns in the cosmic microwave background, then fit those patterns with the standard model, LCDM. L is dark energy. CDM is cold, dark matter. It's the model that explains a lot. Until this number fight. This is where things get strange. Because if LCDM is complete, the early universe prediction and the late universe measurement should converge. The more careful the observations, the closer the answers should get. But Hubble's ladder kept pointing high. Planck kept pointing low. And the deeper scientists dug, the more the disagreement looked like a feature, not a bug. The modern late universe push is closely associated with the H0ES team, led by Adam Rees, using Hubble to refine Cepheids and supernova distances. The early universe anchor is the Planck collaboration and the CMB fit. First clue: the Hubble value didn't wobble randomly. It stabilized around the low 70s across updates. Second clue: the community tried to kill the result the way science is supposed to, by attacking every weak point. Dust extinction, crowded star fields, calibration drifts, selection bias, metallicity effects in Cepheids. One by one, teams tested and retested. Third clue: Planck doesn't measure H0 directly. It measures early universe parameters, then infers H0 under LCDM. So the tension could mean either the latter has a hidden bias or LCDM is incomplete. For years, each side could claim the other side's ruler was flawed. Then came the cliffhanger, a telescope built to see through the excuses. Enter James Webb, JWST. JWST can resolve crowded stars and observe in infrared, where dust is less brutal. If Hubble's ladder was being fooled by blending and dust, JWST should expose it. Here's the reveal. Early JWST checks of key distance ladder targets did not instantly make the tension disappear. That doesn't prove new physics, but it tightens the noose around the simplest Hubble error explanation. When a stronger referee arrives and the fight doesn't end, you start suspecting the rules, not the players. So what's the endgame? 3 theories explain this, and none of them are comforting. Theory 1. Hidden bias in the distance ladder. Somewhere in the ladder, a small systematic error survives every test. Theory 2. A weird local neighborhood. If our region of the universe has an unusual density feature, local expansion could look faster. The idea exists, but it has to match the large-scale maps, and the required bubble may be hard to reconcile. Theory 3. New physics. Something about the universe's energy content or gravity is different than LCDM assumes. A popular candidate class is early dark energy, a brief extra energy component in the early universe that changes the inferred expansion history. Think of it like a temporary turbo boost. It doesn't dominate forever, but it changes the trajectory enough that the numbers stop fighting. Theory 3 is the forbidden secret angle, because it implies the universe had a behavior we didn't write into our model. Yet, the model still looked good enough that we didn't notice. It's like a car with a hidden turbo. Planck reads the blueprint and predicts its top speed. Hubble clocks the car on the road and sees it going faster. Either the speedometer is wrong, or the car has something under the hood. But don't misunderstand the stakes. This doesn't automatically mean the Big Bang is dead. LCDM explains a huge amount. The tension is a crack that might force upgrades, not instant collapse. Just when you think it's a clean 67 versus 73 showdown, another twist hits. Other rulers don't all agree either. Some methods land closer to Planck. Some land closer to Hubble. Some sit in between. That doesn't make the tension go away. It makes it deeper, because it means the universe is forcing us to audit every method we trust. Alternative distance anchors like the tip of the red giant branch, strong lensing time delays as cosmic clocks, and BAO as a large-scale ruler all add evidence, but not a single clean verdict. And now, JWST adds another layer. Deep JWST surveys have sparked debate about galaxies appearing bright and massive very early, which may or may not require model updates depending on how dust and stellar populations are interpreted. So maybe we're seeing one big theme. The early universe was different enough that our simple model needs extra terms. Or maybe we're seeing the limits of precision measurement, tiny biases that only appear when you demand 1% answers. That's why NASA won't explain why feels true to people. Not because NASA is hiding data. These results are public and debated, but because there isn't one official why yet. There are competing hypotheses, and the evidence is still being built. This matters because H0 isn't trivia. It's a master dial. It shapes how we reconstruct cosmic history, ages, growth of structure, and how galaxies like ours became possible. It also connects to the dark sector. Most of the universe isn't atoms. If the solution is new physics, it likely lives where we already know we're blind. Dark matter, dark energy, or gravity itself. The hopeful part is that this mystery is testable. Science is doing what it does best, building independent checks until the truth has nowhere left to hide. Gravitational waves standard sirens, bigger supernova samples, improved lensing surveys, and next-generation sky maps are all on the way. Every one of these is a chance to either crush the tension or prove it's the real deal. And this isn't the only cosmic crack showing up. Next, we'll tackle JWST's early galaxies, dark energy's weird behavior, and how gravitational lensing lets us see invisible matter. Hubble's endgame wasn't a pretty final photo. It was a contradiction that dared us to fix our story of reality. Stay curious. See you in the next one.